In this video, we're going to cover the notes for section 10.1, arcs and sectors. These are two parts of circles that you're going to find measurements of. There will be another one called segments, but we'll get to that. First, we need to define or understand what a central angle is. So a central angle is an angle formed by two radii with the vertex at the center of the circle. So essentially, if you have the center of the circle and then radii coming out, this is a central angle. Now this angle across here is also a central angle. So we need to indicate which central angle we are talking about. And these intercept arcs. So this arc is the distance on the circle from A to B. Now we have a minor arc here. Okay, so that's a minor arc. And we have this one that goes through point C. That's the major arc. Okay, and the notation, if you look, is arc AB, and then arc ACB says, oh, you've got to go through that point C. That's the larger one. Okay, so that's central angles and arcs. To find the degree measure of an arc is equal to the measure of its corresponding central angle. So if I asked you for the measure of arc AB, the degree measure of arc AB, that's 95 degrees. Okay, now it's the length of AB is a little bit different, but that measure is the same as the interior angle, and so the measure of arc ACB will be 360 minus 95, so that's 265 degrees. So that's what we need to know and we need to understand about arcs, central angles, and the degree measure of those arcs. Okay, so here's the concept here. The measure of an arc is equal to the measure of its corresponding central angle. Congruent central angles intercept congruent arcs. So here we have this this angle and this angle are congruent, therefore these arcs are congruent. Or if these arcs are congruent, then those angles are congruent. Now we are going to find the arc length. So this is not a degree measure, this is an arc length. So we have a degree measure of the arc, and we are going to find it by using the circumference. Okay, so here's how I like to think this. Arc length equals the circumference times the portion of circle we have. So what that corresponds to, so arc length equals 2 times pi times the radius, that's the circumference, times our degrees over 360. So if we have a circle and let's say this is 85 degrees with a radius of 7, we can find the arc length. So 2 times pi times our radius times 85 degrees over 360. Now this part just makes sense. If we had half the circle, 180 over 360, then we would expect to have half the circumference. We have 85 3/60ths of the circle, and so we expect to have that much of the circumference. So if I enter this into the calculator, I should be able to get my answer. So 2 times pi times 7 times 85 divided by 360. So this arc length, AB, equals 10.38 units. So here's the formula I just gave you. It did the n over 360 first. We're not going to worry about radians. Radians is another way to measure angles, but we'll leave that for you to learn more about in Algebra 2 next year. Okay, what is the length of AD? So here's the arc length, AD, and it says express our answer in terms of pi. Well, what we need is we need to know the central angle, so we need to figure out n degrees because that'll give us the arc measurement, and we have the radius, and then we'll just plug those into our formula. So what we will do is we are going to take those other angles, so the 104 plus 73 plus 43, and that equals 220. We'll subtract that from 360, and that should give us 140 degrees. So I'm going to write that. The arc measure is 140 degrees. So I've got 140 over 360, that's the portion of the circumference we have, multiplied by the circumference, 2 times pi times 4. That's our radius right here. So I'm going to go on the calculator. Now it says to put this in terms of pi. What that means is we don't multiply it by the pi. So we do all of our numbers and we get 3.1 times pi, and that's my answer. We could take this and multiply by pi and get an answer that would, the decimal approximation is 9.77, but that is the arc length. Now let's find the area of a sector. So arc length is the length along the circle. Area of the sector is like a pizza slice. This is the area of this whole section of the circle. The setup is very similar. We want to take that angle, so we're going to use our 78 over 360. That's the portion of the area, and for the area we're going to use pi times radius squared. So let's write this formula out again. We're going to go n degrees over 360 times pi r squared for the sector of a circle. And that's what we did here. So I'm going to put that into my calculator. And this gives me approximately 68.07. So that's the area of the circle. Sorry, the area of the sector of the circle. Now you'll need to be able to know how to do that. You'll need to find the arc length. You'll need to find the area of the sector of the circle. And there's one more, that's the area of a segment of a circle. The segment of the circle is the part bounded by an arc and a segment joining its endpoints. Okay, so it's this region right in here. This is the segment of a circle. Notice the further away the points are, the bigger that segment will be. But here's how I like to reason how we find this segment. What we'll do is we'll take the area of the sector, and then we subtract the triangle, and that's going to equal just that segment. So we know how to find the area of a sector. In this problem, it would be 60 over 360 times pi r squared. That's times 64. Minus the area of a triangle. Now looking at this triangle, there are a few ways we could do this. One, we could use trigonometry. We could cut this in half and then find the lengths of the sides. Use our right triangle trig. What I'm going to tell you now, well, let's do that. And then I'll show you a shortcut if you choose to remember that. So I'm going to cut this in half. So this is a 30 degrees, and this is 8. Now this is a 30, 60, 90, so I don't even have to set up my trig ratios. I know that this side here will be 4, and this will be 4 square roots of 3. So the area of this particular triangle is 8, because this side's 4 and this side's 4, so base times height divided by 2. 8 times 4 square roots of 3 divided by 2. And I can put that into my calculator, and that will give me the answer. So I found the area of the sector, and the area of the sector was 31.416. And then I'll go 4 times 4 square roots of 3. And this gives me 27.713. And I'll subtract those, 31.416 minus 27.718. And that gives me, we've approximated this now, 3.698. Now, I told you there was a shortcut. Students in previous years have found this to be very helpful in this type of problem. So let me tell you one of the ways to find the area of a triangle. And you've never learned this before because it deals with trig functions. If you know an angle theta, and you know the two sides right next to it, you can find the area of the triangle by going 1/2 a times b sine of theta. The really nice thing in this application is because a and b are both radii, they're the same. And because this is a central angle, we have to have the central angle anyways. And so we already have the information here. And so I can go 1/2 times the radius squared, 64, times sine of 60 degrees. And I verified that on my calculator. That gives me the exact same value, 27.713. And so, to find the area of a segment, the general formula that I would use is, I'm going to use theta over 360. Theta is a Greek letter that we use for angles a lot, if you remember from our last unit, times pi r squared minus 1/2 r squared sine of theta equals the area of the segment. If you want to find the area of this triangle by using your trig functions, you may do that. That works just great. So that finishes up this video on section 10.1. Thank you for watching.